Hello and welcome. In this video, we're going to come full circle to when we first introduced limits, and that was looking at the tangent, slope, and velocity problem. Now that we've learned a lot about limits, we can come back to that, and we can actually come up with a brand new definition for what we call the derivative of a function. So we'll start off with a definition for the derivative of a function at a number a, and then quickly we can turn that into its own function. Let's start off with the derivative as just being a value. The derivative of a function at a number a. We define that as follows. F prime of a, so it's an f with a little tick mark at a point a, is equal to the limit of f of a plus h minus f of a divided by h as h approaches 0, provided that that limit exists. Now remember where this comes from. This formula came from when we were trying to look for the slope of a tangent line at a point P on a function y equals f of x. And so we're going to be looking at a specific number a, and so P is going to be the point a comma f of a. And the tangent slope that we're looking for is the slope of a line that just touches the point P and just grazes the function right there. This can be thought of as the instantaneous rate of change of the function at that point. Now, in order to do that, we had to pick a second point on the curve, and let's call that point Q. Now, we'll travel just a short distance away from A. We'll call that distance H, and this point Q would then be at A plus H, comma, F of A plus H, and H could be positive or negative, and that would change whether Q is to the right or to the left of point P. And then using the slope of the line from P to Q, we get a very close approximation of the slope of the tangent line. And remember, MPQ is just the slope from P to Q, which is y2 minus y1 divided by x2 minus x1. Now that's just going to be a plus h minus a, which is where we get a difference of h. And that part there is actually just the difference quotient. And as we take the limit as h approaches 0, we move q closer to p, and we get the slope of the tangent line. So the derivative of a function at a number a is really just going to be the same value as the slope of this tangent line. That's one way to think about it. It's also the instantaneous rate of change of this function. And if our function represents position, the instantaneous rate of position will be velocity. So there's lots of uses for the derivative. This isn't the only definition for the derivative of a function f at a number a. There's also an alternative way to actually write this. An alternative definition for f prime of a, the derivative of f at a number a, is to just make q have the coordinates x comma f of x instead of using a plus h. And the only difference is that if we let the coordinates of q be x comma f of x, we take the limit as x approaches a. And so this is an alternative way to look for the derivative. But it's everybody's personal preference as to which you prefer. My personal preference is using limits as h goes to 0. Now let's try using a very simple function, but look for the derivative to come up with the slope of the tangent line. And from there, we can even form the equation of the tangent line. Okay, well, let's start off with a nice looking function such as a quadratic. F of x equals 3x squared minus 2x. Now, first of all, let's just see if we can evaluate the derivative of that function at the number 2 when x is equal to 2. And that's going to lead us into our second part here of giving the equation of the tangent line to f at that same point where x equals 2. Okay, so we're going to be looking for f prime of 2. So letting our a change from a to the number 2 in this example. Well, we're still going to have the limit as h goes to 0, but now we'll have f of 2 plus h minus f of 2 divided by h. Now, just be careful here with some function notation. F of 2 plus h here, which I've just changed to black, is going to be making sure that we just change all of the x's in our function to 2 plus h's. Now, of course, every x needs to be replaced with 2 plus h, so we may have to do a little bit of work here to simplify this entire expression. What's a little bit easier is just plugging 2 into our function, and that is what the meaning of f of 2 is. So we're going to be subtracting and plugging 2 in. We'll have 3 times 2 squared minus 2 times 2. Now at this point in time, it's very important to make sure that we're subtracting that whole value. So we should evaluate it first, put brackets around that, and then subtract the value. Now all of that will be divided by h. And if you've not already noticed, we can't just plug 0 in yet. We're still going to have to wait to simplify this before we can take the limit and evaluate it. So simplify the top by expanding, and then let's see if we can do anything about the h. Now you'll notice once you've expanded everything out here that we'll have a few things that can cancel out. And that would be in this case 12 minus 4 minus 8 all cancel out. That's going to be really handy because every one of the remaining terms has an h. We can collect those terms together, factor an h out, and that's going to help us to simplify. Now, when we get to the step where h's can cancel out, now we're going to end up with an equivalent function, but this equivalent function, 10 plus 3h, doesn't have the same restriction on its domain. So it's fairly equivalent. It's the same as our original expression, except for the fact that h equals 0, we can just plug in now. So at this point in time, when you evaluate the limit, then we can just write down a value by plugging in 0. And we end up with 10. So how does that actually help us? Well, 10 tells us that at this particular number, x equals 2, our function is increasing. It has a slope of 10. That's the slope of the tangent line, but it's also going to tell us how quickly the curve is increasing as well. And then, why don't we go ahead and complete this and give the equation of the tangent line. Now, to form the equation of the line, we need two pieces of information. We need the slope of the line, m, but that's just the same thing as f prime of 2, because it's the slope of the tangent line, and so we know that m is equal to 10. We also need a point on the line. That point could be the y-intercept, and that would be really convenient, but we can see that this is not a y-intercept that's given to us in the question. It's a point where x equals 2. So if x is equal to 2, let's say that that is x naught. What is y naught? Well, we can just plug 2 into the function. And actually, we did that earlier. You can see in green here, we already evaluated f of 2, and we saw that it equaled 8. So this means that we have a point on our line, x naught, y naught, is equal to 2, 8. And with those pieces of information, we can use the point slope form of the equation of a line. Y, which would be any y value on the line, minus y naught, which is the y coordinate of the point, is equal to m times x, which is the x coordinate of any point on the line, minus x naught, which is the point that we've just been given. Plug all this information in. Y minus 8 equals 10 times x minus 2. And we've got the equation of the line in point slope form, but it's not necessarily the easiest form if we wished to kind of graph this. We could then rearrange this and expand out y, add the 8 to the other side, would be equal to 10x minus 20, and don't forget to add that 8 over there. So y is equal to 10x minus 12. And we can see right now that we have a y-intercept of negative 12 with a slope of 10. If you have software like Maple, or you have a graphing calculator, or you have some other internet-based graphing software like Desmos, then you can try plotting both this curve and the line, and you should see that they are tangent. Okay, now let's expand this concept a little bit. Instead of talking about the derivative of a function at a number a, we can just talk about the derivative of f in terms of arbitrary x. Now the definition is roughly the same. The only change here is we're going to change a to be an arbitrary x. And it may not always exist, but we can take a look at that as well. Okay, so this is really one of the biggest definitions, probably one of the most important definitions of first semester calculus, and that's the definition of the derivative. We say that the derivative of f with respect to x is the limit of f of x plus h minus f of x, all divided by h, and then we take the limit as h goes to 0. And even though we're going to be looking at a variety of shortcuts, so many shortcuts to be able to calculate the derivative in more useful ways, every one of the rules that we're going to be introducing in the future here to make our lives a lot easier is all going to come back to this definition. So don't forget it. It's definitely going to be something of great importance, and you'll see it again even in second semester calculus. So the change here you can see is x has been replaced with a. And now we have a way to calculate the derivative at any value along the x-axis. Now, not every single point along the x-axis, not every single value of a is necessarily going to make this limit exist. So we're going to come up with a little definition here. We say that if this is a value that exists at a, then the function is differentiable at a. And we can even expand that. There might be an entire interval of x values that for every one of the values in that interval, it would be differentiable, in which case we could say that the function f is differentiable over an entire interval. And so we've got a little definition for differentiable at a single number and a definition for differentiable over an interval. And now we can start talking about the derivative of a function at any single point on the x-axis. And if we use this definition, we can calculate f prime of x and then just plug numbers in as we want to find the instantaneous rate of change of the function at any value where it's differentiable. Okay, we have a function f of x. X cubed minus 2x squared plus x. Let's see if we can find the first derivative using the definition. We're going to be taking the limit as h goes to 0. And the first thing we'll do is take all of the x's and replace them with x plus h's. That will give us f of x plus h, and then we're going to have to subtract f of x. But make sure that when we subtract f of x, that we subtract every term. And it's best to maybe use square brackets here so that we know to subtract each term by changing their signs. And the entire numerator is over h. Now at this point in time, maybe it's best to pause the video and try some algebra. Try expanding out all of the terms on the numerator and collecting them. And you're soon going to find out that some of the terms are going to cancel out and simplify. Pause it now and you can come back here in just a moment and continue onwards. I'm going to skip to the next step where the entire numerator has been expanded. Okay, how did you do? It expands into quite a mess here. But we're going to find that x cubed cancels with minus x cubed. We're going to find that negative 2x squared cancels with positive 2x squared. We'll find that positive x cancels with negative x. And you can start collecting any other terms that you see in common. But you're going to notice right away that every term that is remaining has an h. And that's going to allow us to cancel out a factor of h from the numerator and the denominator. So again, try some algebra out on your own here. Simplify this and see what you can come up with. Now, the moment that we can cancel out h's, we can then evaluate the limit as h goes to 0 by plugging 0 in for all of the h's. And what we should end up with now won't have any h's remaining. It should only have x's. 3x squared. Skipping the terms here that go to 0, we just have minus 4x plus 1. And so, unlike when we take the derivative evaluated at a number, what we end up with is f prime of x is a function of x. And now that means that we can even look at the graph of f prime x. And from plotting both of these, then we can kind of establish some patterns for graphing the derivative from an original function f. Okay, if we wish to plot the function f of x equals x cubed minus 2x squared plus x, it might be useful to try factoring it to see where its x-intercepts are. Now, once you try factoring, you'll find out that the factors are x and x minus 1 squared. That means that x equals 0 is an x-intercept, and x equals 1 is another x-intercept, but x equals 1 is a repeated intercept. So our function is actually just going to touch the curve there. This kind of information might help you to graph the function, but when in doubt, you could always try using Maple or some other software. Now, being a cubic function with a leading coefficient of 1, we could even use a little bit about limits as x goes to infinity to understand what happens at both tails. If we take the limit as x goes to positive infinity, then we can see that this function is going to also endlessly increase in the positive direction. So our function is going to travel off the graph upwards and to the right. If we take the limit as x goes to negative infinity, however, then our function becomes infinitely large in the negative direction. So our graph is going to come into this area from the bottom left. It will cross through the first x-intercept, and because the second one is repeated, it's just going to touch the x-axis there and then travel off to infinity. We have a pretty good idea of what this graph looks like. Now, what does the graph of its derivative look like? The derivative, if we think about its shape, is just going to be a parabola. And it's a parabola opening upwards because it has a leading coefficient that is positive. We can also take a look at its x-intercepts and get a pretty good idea of what that graph looks like. When we factor f prime x, we see its factors are 3x minus 1 and x minus 1. So it would have x-intercepts at x equals 1. Now I'm going to keep the same scale as before. So it has an x-intercept at 1, 0. And it also has an x-intercept at 1/3. And of course, since it's a parabola opening upwards, we have a pretty good idea of what the shape of it would look like. Now, I've drawn these two graphs so that they have the same scale for the x-axis, and I've also tried to line them up perfectly above and below each other to show a couple features here. There is an association between the x-intercepts of the derivative and features of the original function. Because remember, f prime of x is the instantaneous rate of change of f. So looking at the blue function, I'm just going to scribble over it a little bit here, so bear with me. We can see sections of this curve where the function is increasing. So this particular blue section is increasing, and if we take a look at where it stops increasing and it becomes a maximum, we can actually see that that corresponds to this particular x-intercept right here. Now we say that something is increasing when it has a slope that is positive. And then we can also see that during this particular section, the red curve is positive. If we go back to f, in the next section here where it's definitely going to be decreasing, wherever that function is decreasing, we can see that the function's derivative is negative. So traveling over a little bit further, we can see that in this next segment, f is decreasing, so it would have a negative slope for its tangent. And during that particular section, the function, its derivative here, is also negative. So we can label anything that's increasing on this blue curve as being positive on this red curve, and anything that is decreasing on this blue curve as being negative on this red curve. And finally, the last section of our function is back to being increasing again. Whenever something is increasing, we can see that the derivative is positive. Now, most importantly, the x-intercepts of the derivative. They occur at x equals 1/3 and x equals 1. And those are precisely points on the blue curve where we see that it has a slope of 0. There are two coordinates where we see that the tangent would be a horizontal slope, and those correspond to these two blue dots here on the derivative. So it's pretty helpful if you have the graph of any function to find out where it has a slope of 0, and those will become the x-intercepts of the graph of its derivative. Now, in the case of this function, f of x equals x cubed minus 2x, we can see that at any point on this curve, we should be able to find the slope of the tangent line. So it would seem that this function is differentiable over all real numbers. What does it mean for a function to not be differentiable? Is there an example that we can think of for a function that has a point where the derivative doesn't exist? Well, there's a couple situations where that can happen. The first one would be simply that a is not in the domain of the function. So, a little example of a graph. If we have a function that is non-defined at a here, then of course, trying to compute f prime of a would involve using f of a in our limit definition. Since f of a is undefined, we can't plug that in. So obviously we can't compute the value of f prime a. But that's not the only circumstance. Another case where f prime of a does not exist is when we have some sort of sharp corner or a cusp in our function. So another graph is going to be useful here. In the case of this kind of graph, we would have some sort of function that has a sharp corner. And that would have to be occurring at the value of a. Now, why would this cause a problem? We'd have to, again, think about the definition of the derivative at f prime a. Now, this limit definition is a two-sided limit. So we also have to consider that we need to look at the limit as h approaches 0 from the right and from the left. Now, imagine taking a point slightly to the right when h is positive. Connecting these two dots together, and we'll get a slope of a secant line that is a pretty close approximation to the slope of the tangent line. And that would be this blue line here, that secant line. Now, what if we were to take h as being a negative number? That would give us a second point slightly to the left, and that would give us the slope of the secant line, which is in green. And as we take these points and get them closer and closer to a, you can see that their slopes are never going to agree on the same value. And because the slope when we come from the right is different from the slope as we come from the left, we can't actually say that the two-sided limit exists. We can only say that maybe each of the one-sided limits exists, but we don't have a derivative. So we would say it's not differentiable at a cusp or a corner. And even this isn't the only example of a potential problem. Another potential problem, even when a is defined, is when the slope becomes so steep that it approaches vertical. Let's think about a graph that might have a vertical tangent line. Some sort of function that would just, for a brief moment, appear to be vertical, but still pass the vertical line test. There would just be a single point here that if we approached from the right or from the left and we use the limit definition, that this limit approaches infinity or gets endlessly large, possibly negative infinity. But of course, this limit doesn't exist. Infinity is not a number, and so f prime of a does not actually exist. So it's an undefined slope, just the same way that a vertical line has an undefined slope. And so these three cases are when a function is not differentiable. Now, we can take a look at some applications of the derivatives in another video, but hopefully this gives you a little bit of an idea about finally wrapping up the purpose of limits for right now. It's so that we can evaluate the instantaneous slope or instantaneous rate of change of a function. And the easiest way to do that is to leave our derivative in terms of x, and then we can plug in any value of a that we wish, so long as it is differentiable at a. And that will give us how steep the function is, whether it's increasing or decreasing or horizontal in the case where the derivative equals 0. So stay tuned for the next video, because then we'll take a look at higher power derivatives and a little bit more of some interpretations of what the derivative means. Thanks for watching, and I'll see you guys in the next video.